up tonight?
No, we're preparing a presentation on nanotechnology.
Oh, neat.
Yeah. At the phone. And then we stayed at the Balthazar until closing. Just working on a nanotechnology presentation. Fascinating. You're joking. All he thinks about is weightlifting. We need more info.
Hey, fellow atoms, come over here, this way. I've got something to tell you. I've got news. The people in the world above us are starting to get interested in us atoms and not to split us.
It's about time!
What's more, 2 students have to do a presentation on nanotechnology. But they can't find enough information.
But who's going to help them? Me!
And me.
Oh, don't be scared, Lola. It's just me, Nano, and this here is Nina. Hey, what are you making that face for?
Hello, sweetie.
And this must be Jack the Muscle Man. Try working that muscle that's in your head, my boy.
Oh, look, you've hurt his feelings. The poor darling.
I'd hate to spoil the fun, but your presentation still needs a lot of work. Luckily, we're here to help you.
Well, it looks like they've made contact. That's good.
Those grapes look nice.
But he could at least tell them what nanotechnology is, couldn't he?
All right, kids, here goes. Where to begin? Nanotechnology is the technology of 1/1000th of a metre. It's the technology of atoms.
And that's us.
Hey! Don't eat me.
I need some water.
It talks. All right, there's no time to spare. If you want to finish your presentation, get up at 7 o'clock tomorrow morning and get to the lab, OK?
We'll show you the best experiments around. See you later!
I dreamt about atoms all night.
About us? Oh, that's so sweet.
All right, that's enough. Let's get to work. In Greek, nano means dwarf. That's why scientists chose the word to represent...
1/1000th.
That's it. 1/1000th of a millimetre is a micron, and that's the size of bacteria.
I know. And 1,000 times smaller than nanometer.
That's right. 50,000 times smaller than the thickness of one of your hairs, my dear. It's the size of a few atoms. Great, isn't it?
Hey, look. You can see me, right? Well, it's because I've been increased in size 1 billion times. If we were in proportion, you would be 2 million kilometres high, 5 times the distance between the Earth and the Moon. You have no idea what goes on in our little world down there. It's full of atoms, so many atoms.
We are the atoms! We are the atoms!
We're everywhere!
Hello.
Hello.
Hello. Let's go and talk about nanotechnology. Before moving on to nanotechnologies, you should know that electronic components have become increasingly small and increasingly powerful. We've moved on from the valves that were inside our grandparents' radios to semiconductor components in electronic circuits. And finally onto chips which contain millions of transistors. With the help of a clean room electron microscope, I can actually show you one of these chips. You should be aware that the slightest speck of dust can pollute our work. The reason we filter the air constantly and pressurize the room is to ensure that dust doesn't get inside.
Believe me, what he's saying is true. For you, dust is no big deal. It's tiny, nothing. But for us atoms, the slightest speck of dust is enormous. For you, it would be as big
The
as...
Himalayas.
Oh, that's it, the Himalayas.
This is a microchip. The chip itself is nothing more than the small dark plate you see in the center. You can find them everywhere. In computers, in mobile phones, information can be stored in them. Tons of information. A single chip can store up to 25 volumes of the Encyclopedia Britannica. For research purposes, we use electronic microscopes. Over here, you can see a group of microchips. We're going to enlarge the picture to see silicon nanocrystals. This microscope can magnify up to 800,000 times. So now you know what a microchip looks like, but today in the laboratory we're working on nanochips. The one represented here has been enlarged 60,000 times, and now 240,000 times. And this measures 10 nanometers in diameter, the size of about 100 or so atoms.
So, the smaller the components, the more that can be put on a chip, the more information that can be stored.
Exactly, and the smaller they are, the faster the flow of information. The microelectronics industry has moved from biggest to smallest. In other words, from top to bottom. And we call this approach top-down. So we are miniaturizing. But for the industry, when we reach 10 nanometers, the techniques get too costly. We're reaching the limit. But of course we won't stop there. We want to make things even smaller. But how then? How then?
Start with the atoms.
Start with the atoms?
Exactly. Start from atoms and then build structures that are bigger. That means going from the bottom to the top, or in our jargon, the bottom-up approach.
Yes, but everything around us is made up of atoms. A table, our skin. So, does that mean everything can be reconstituted?
Theoretically, yes, but we still need the necessary knowledge and tools to be able to manipulate the atoms.
And the molecules.
We can create new structures, structures that have never been seen before. These materials that we call intelligent have novel properties such as, for example, functionalized surfaces. If you graft onto a surface molecules which are extremely hydrophobic, in other words, water repellent, you create a self-cleaning surface. But why? Because since the water doesn't adhere to the surface, it takes the dirt away with it.
It's a similar principle as to why lotus leaves always remain clean and dry.
Precisely. The leaf's surface is nanostructured, so water doesn't come into contact with the leaf. It rolls off, taking the dust with it.
Mm-hmm.
But I have other examples to show you. Follow me. Here are some applications. On normal glass, water adheres and spreads. But now let's see what happens with a nanostructured surface. The water bounces right off.
No more dirty windows. And no more wash basins to clean.
Exactly. And look here, a steel scourer scratches only the right side of this bodywork part, because the left side is nanostructured. By making the surface perfectly even, the coating is hardened, making it completely scratch-proof. Today, we can manufacture windows whose transparency can be modulated electrically. And the glass you see here, its structure was worked on a nanoscale, rendering it hyper-insulating even at extremely high temperatures. I've shown you some ways nanotechnologies can be put into practice. This approach to matter starting from atoms presupposes that we can see them, and we have the tools.
This is one of the microscopes of the 21st century. Its inventors received the Nobel Prize. It's the tunnel effect microscope. It is indeed based on the tunnel effect, which is a quantum phenomenon. Have you ever seen a ball go through a wall?
No.
That's because in classical mechanics it's impossible. However, on an atomic scale, electrons can cross barriers which they cannot theoretically go through. That's the tunnel effect. This effect is used to probe the surface of materials on an atomic scale. The point you see is the heart of the microscope. You move it parallel to the surface of the material studied, which must be an electricity conductor. Whenever the extremity of the point goes over an atom, electrons pass as a result of the tunnel effect from the sample to the point. This generates a mild current, which becomes more intense the closer the point gets to the atom. The tunnel current is converted by calculating in terms of altitude, and thus, point by point, line by line, a topographical image of the surface is reconstructed. The image is accurate. We can actually see the matter on an atomic scale.
It's true, it's fantastic, isn't it? Human beings can finally see us with their tunnel effect microscope. At last we've got visitors. Smile, you're on camera.
And now, here are some surfaces visualized in atomic terms. But there's something even more extraordinary. Not only can we observe, we can also act upon matter on an atomic scale. By giving the point an electric charge, the atoms can be moved one by one.
So it's the sharpest, most precise engraving system in the world.
That's the idea. We work atom by atom.
And then from atoms we can create bigger objects, like using bricks to build a house. In this approach, we start at the bottom and then move up.
Bottom up.
Right. Everywhere, researchers are working to invent new minuscule objects, which resemble everyday objects, cages, wires, tubes, not with microscopic
But
dimensions.
nanoscopic.
She's got it.
This sort of research sounds fun.
It's more than fun, it's amazing. For example, using carbon atoms, we can create structures that have never existed, that have never been seen before. But I'll let one of my colleagues tell you more.
Look, he gave me a floppy CD. It's a spin-off of Nanotechnology, and you can put 20 hours of music on it.
Yeah, we'll be able to dance all night to just one CD.
What does dance mean?
Oh, moving your body in time to the music. Step back away, step back away. We heard you study carbon objects that don't exist.
That have never been seen. These are carbon nanotubes. In fact, they are original assemblies of carbon atoms. Carbon can be structured in completely different ways. For example, here, on one plane, there are carbon atoms which form hexagons. This generates a planar structure. These are graphite layers which can slide one on top of the other. In that way, we can obtain lubrification properties that are very interesting. But if we take this other structure here, the carbon atoms form small tetrahedras which are repeated in 3 dimensions of space. Of course, I'm referring to diamonds, which are extremely hard and impossible to deform. Very recently, we've observed new forms of carbon, and this is one here on the screen. What does it remind you of?
A football.
Yes, that's right. And its inventor won the Nobel Prize for this discovery. In fact, this molecule, which is known as C60, is made up of 20 white hexagons and 12 black pentagons. It has a very particular topology. Its name comes from the 60 types of carbon on its sphere. So carbon nanotubes are in actual fact a variety of this C60 molecule. This molecule here will give you a better idea of what the molecule looks like. In order to create it, all you have to do is take the graphite plane and roll it into a cylinder.
And nanotubes have extraordinary properties.
They're more resistant.
And lighter too, but I'm sure he'll talk about them. You'll see.
The dimensions of the nanotube can be seen very clearly. It has a diameter of just a few nanometers. The length is 10 microns, and on an atomic scale, a micron is very long. But on a human scale, of course, this nano object is about 100,000 times finer than a hair. Here, we'll examine the extraordinary stability of nanotubes when they're placed in different experimental conditions. This is where carbon nanotubes are produced. Their synthesis requires very high temperatures to recombine the carbon atoms. And Hanako here is measuring the temperatures by means of pyrometry. The gas being injected is acetylene, which is the source of carbon. Once the nanotube sample has been produced, we're going to measure it in another part of the laboratory. Here we are. This is where we measure the physical properties of carbon nanotubes. That's the work of the experimentalists. The carbon nanotube is one of the most resistant materials made by man. When woven in the form of fibers, it's 6 times lighter than steel and 100 times more resistant. Come and look at some possible applications. So, in terms of applications, researchers who are very imaginative are already thinking about lift cables for space. But there are also more common applications that are more concrete, such as bone prostheses. And since they're made of carbon, we think they would be perfectly biocompatible.
Our body wouldn't reject them like certain grafts.
Precisely.
But there's a problem. Working atom by atom when there are billions in 1 milligram of matter, it would take ages.
Yes, the age of the universe wouldn't be enough. And that's why we're exploring a path which is absolutely necessary, self-assembly. Getting the work done by the atoms themselves or by the molecules. That's why chemists and biologists need to work together.
Here, we're trying to understand the laws of self-assembly of macromolecules. We try to find ways to get them to position themselves in the exact place we want them to be. In practice, we proceed in stages. We start from a surface on which molecules form a two-tone layer of zones with different properties. Then we send in molecules which recognize one of the colors and attach themselves electively. Next, we send in the second wave of molecules which land on top of the first ones, and so on.
Yeah, like a big set of Lego.
Exactly. Once we master this type of technique, we'll be able to establish interfaces between the electronic circuits which contain the layers and biological tissues, or large molecules.
Does that mean we could even hook up living systems to computers?
That's right. And it's already underway. Look here, for example, at the image of a snail neuron which has grown on an electronic chip. And the information, the current, passes between them.
But what's the purpose of associating computers with biology?
Well, to enable the blind to see, to enable the deaf to hear, to adapt the administration of medicine in situ, according to the state of a patient, that sort of thing.
So for nanotechnology, you have to be a chemist, a biologist, a physicist, and an electronic engineer.
Exactly.
Without forgetting ethics.
And the environment.
Of course.
Hey, but can we make a bunch of grapes?
No.
Oh.
This is where we carry out our self-assemblies by stages.
Does that mean that everything that's alive is self-assembled?
Yes, all living things, like plants and animals, even bacteria. Our own cells are self-assembled. And today, researchers are attempting to build similar systems artificially, on the basis of these principles. But there's something even more amusing. Living matter. It moves, it swarms, and the nano world is no exception. There are parts that move about. For example, what you see here are bacteria flagella, which enable bacteria to move around. Nanomotors are what enable the flagella to move.
It's the same as for the tails of spermatozoa.
Yes, indeed. And understanding the laws of these natural supramolecular self-assemblies is the work of the researcher. They can then use them as models to create similar artificial systems. This is known as biomimetics. And today, we've already invented nanomotor parts that were copied from life, which operate in the nano world. For example, these atoms seem to be simply resting on a nanotube. When, snap, you've got gear wheels. Now here's something. We've got a kinesine molecule that's moving all on its own, on a microtubule. And the ultimate goal is to create nanomotors.
Like in nature?
Right. This is a good example. A medium, an enzyme, a blade of a few nanometers, and snap, you plunge everything into an energy solution, and it works. And now for the real thing, filmed under a microscope. It could be an engine operating a nano workshop. And they could even operate inside us, within our very own bodies.
Inside us?
Yes. We're beginning to dream, to imagine nanorobots that could seek out and identify infectious cells and destroy them, eradicate them. More realistically, we're making nanoparticles that are themselves medicinal or that can extract the virus.
So, what's happening tomorrow?
Tomorrow, young lady, we're going to go surfing on the internet. There are already several schools, universities and courses that are opening all over Europe. Come on, let's dance. Do wap be ba ba wap ba ba ba. Hello there, you guys. I found something amazing. There's a great thing at the moment in Grenoble. Come on, follow me. Yeah! Whoa! Hey! Whoa!
And this is how we will be able to obtain images of atoms or surfaces.
Check it out, kids. The students here are looking into a tunnel effect microscope.
On the left and the sample on the right.
Yeah, it was good.
It was interesting.
Yeah, it was interesting.
They're experimenting with the enlargement of micro-engines.
Take a look and you'll see some patterns emerge. And what we are going to do is initially move...
A practical application. The making of a plate of nanochips.
On the hot plate. Someone should stand aside to press the little red button. Move the hot plates. And what's more, they're starting new courses at university. Follow me to Copenhagen, okay? Here I go. Ouch!
I went to the homepage of Copenhagen University and saw that it was a combination of all the classical sciences, math, chemistry, physics, and it appealed to me.
Working as a natural science has a lot of resemblance to working as an artist, maybe even more than working as a technologist, because it's our fantasy, our imagination, which sets the limits to what we can do if we want to build something with molecules and atoms. And we are, in a way, artists just as a painter, but we're not working with a brush and paint, where we have our experience from our everyday life that we can use, and the impressions we want to give are impressions we know from our everyday life. First, we have to learn the rules that the molecules and atoms, they live under, and then when we've learned that, then we can express ourselves as artists working in that world.
Hi there again. It's all up to you now, and good luck with your presentation. Ho-ho!
The presentation we're giving today is on nanotechnology. I don't know if an hour will be enough to tell you everything, but we'll try to give you a feel of how fascinating the nano world can be.
What is nanotechnology? What will it contribute to society, to our health, to industry, and the environment? In what ways will it help us to improve our lives? What challenges and uncertainties will this new approach engender? That's what we're going to talk about today.
See you soon!